In our quest for a new home among the stars, the universe offers tantalizing possibilities. Welcome to episode 3 of The Search for a New Home. January 2023. NASA announces a discovery that changes our understanding of potentially habitable worlds. TOI-700E, the second Earth-sized planet found in the habitable zone of the same star system. Not just another exoplanet, not just another Earth-sized world, but the second potentially habitable planet orbiting the same star, making TOI-700 one of only a handful of systems where we've found multiple small worlds in the Goldilocks zone. This is the story of how we found it, what makes it extraordinary, and what it means for humanity's search for life beyond Earth. 100 light-years from Earth, in the southern constellation Dorado, a small red star hosts an entire planetary system we never expected to find. TOI-700, a cool M dwarf star, roughly 40% the mass of our Sun, with a surface temperature of about 3,500 Kelvin, significantly cooler than our Sun's 5,800 Kelvin. Around this dim red star, for planets orbit in a tightly packed configuration. Planet B, the innermost world, completes an orbit every 10 days. It's about 90% Earth size, likely a scorched rocky world baked by proximity to its star. Planet C, the second world, is a super-Earth more than 2.5 times Earth size. It orbits every 16 days, too hot for liquid water, but fascinating for its composition. Planet D, discovered in 2020, was the breakthrough. An Earth-sized world orbiting every 37 days, sitting squarely in the conservative habitable zone, the region where liquid water could exist on a planet's surface for most of its lifetime. And now Planet E, discovered in 2023 after scientists analyzed an additional year of data. At 95% Earth size, it orbits every 28 days, placing it in the optimistic habitable zone, the broader region where liquid water could have existed at some point in the planet's history. 2 potentially habitable worlds. 1 star system. This is extraordinarily rare. This is one of only a few systems with multiple, small, habitable zone planets that we know of, says Emily Gilbert, the NASA JPL scientist who led the discovery team. That makes the TOI-700 system an exciting prospect for additional follow-up. But here's what makes this discovery even more remarkable. We almost missed it entirely. The Transiting Exoplanet Survey Satellite, TESS, launched in April 2018 with a mission to scan 85% of the sky, searching for planets around nearby stars. The method is elegant in its simplicity. Watch stars, watch them constantly, and wait for them to dim. When a planet crosses in front of its star from our perspective, an event called a transit, it blocks a tiny fraction of the star's light. For an Earth-sized planet crossing a Sun-like star, that dip is about 0.01%. For an Earth-sized planet crossing a smaller M dwarf like TOI-700, the dip is larger, but still incredibly subtle. TESS divides the sky into sectors, observing each for approximately 27 days. It captures images every 2 minutes, building a continuous light curve for thousands of stars simultaneously. In 2018, TESS observed the southern sky, including TOI-700. The satellite detected 3 clear planetary signals. The regular dips of planets B, C, and D. Planet D's discovery in 2020 made headlines. An Earth-sized world in the habitable zone, detected by TESS, confirmed by ground-based telescopes. It was TESS's first Earth-sized habitable zone planet discovery. But there was another signal hiding in the data. A signal so faint, so subtle, that it couldn't be confirmed with just 1 year of observations. In 2020, TESS returned to the southern sky for additional observations. This gave scientists a second year of data for TOI-700, and that's when Planet E emerged from the noise. If the star was a little closer or the planet a little bigger, we might have been able to spot TOI-700E in the first year of TESS data, says Ben Hord, a doctoral candidate at the University of Maryland and NASA Goddard researcher. But the signal was so faint that we needed the additional year of transit observations to identify it. The discovery demonstrates something crucial. We're now capable of detecting Earth-sized planets in habitable zones around nearby stars. But we're right at the edge of our detection capabilities. Planets like TOI-700E require patience, repeated observations, and meticulous data analysis. The extra year of data did something else too. It refined our measurements of all 4 planets, making the size estimates about 10% more accurate than initial calculations. This is how modern exoplanet science works. Not with single dramatic observations, but with accumulated data, statistical analysis, and the gradual revelation of worlds hiding in the cosmic noise. To understand what makes TOI-700E special, we need to understand the system it calls home. The TOI-700 system is centered around an M-dwarf star, a type of star that makes up about 75% of all stars in our galaxy. These stars are smaller and cooler than our Sun, but they have incredibly long lifespans, potentially trillions of years, far longer than our Sun's 10 billion-year lifespan. But M-dwarfs present unique challenges for habitability. Their habitable zones are much closer to the star, meaning planets within these zones are often tidally locked. This results in one side perpetually facing the star, experiencing extreme heat, while the other side remains in eternal darkness and cold. However, a thick atmosphere could redistribute heat, creating a temperate terminator zone between the two extremes. This twilight zone might be where conditions are most Earth-like, offering a stable environment for potential life. Second, stellar activity. Young M-dwarfs are known for powerful stellar flares, which can strip away planetary atmospheres. However, TOI-700 is an older, quieter M-dwarf exhibiting low activity, which is favorable for its planets. Third, the spectrum of light. M-dwarfs emit more infrared light than visible light, which could impact photosynthesis as we know it, but life might adapt to utilize these different wavelengths. Despite these challenges, the TOI-700 system is a prime candidate for habitability studies. TOI-700D, discovered in 2020, is 20% larger than Earth and resides in the conservative habitable zone. TOI-700E, confirmed in 2023, is 95% Earth size and is located in the optimistic habitable zone. Both planets receive significant solar energy, with TOI-700D receiving 86% of Earth's solar energy. The system's architecture suggests remarkable stability. The planets orbit in a near-perfect 8:4 to 3:2 resonance, meaning their orbital periods are precisely synchronized. This stable configuration has likely persisted for billions of years, protecting the planets from chaotic gravitational interactions. The TOI-700 system has had that time. M-dwarfs are ancient stars, and TOI-700 could be billions of years old. If conditions on planets D or E ever became favorable for life, there's been ample time for it to develop. The concept of a habitable zone is both simple and maddeningly complex. It's the region around a star where conditions are just right for liquid water to exist on a planet's surface, a fundamental requirement for life as we know it. Too close, and water boils away, creating a scorching, Venus-like inferno. Too far, and water freezes solid, turning the world into a frozen desert. But the boundaries aren't fixed. They shift based on the star's size, temperature, and even the planet's atmospheric composition. For instance, early Mars might have been a watery world, despite being further out. In the TOI-700 system, planet D orbits squarely within what's considered the conservative habitable zone. Then there's the optimistic habitable zone, a wider region that considers planets with dense atmospheres capable of trapping more heat, or those with internal geological activity. In this broader view, TOI-700E also orbits within this zone, expanding the possibilities for life. But here's the crucial point. Simply being in the habitable zone isn't enough. A planet also needs a stable atmosphere to maintain liquid water, a magnetic field to protect it from stellar radiation, and geological activity to recycle nutrients and regulate climate. Furthermore, the right chemical ingredients, like carbon, hydrogen, oxygen, and nitrogen, must be present, often delivered by asteroids and comets. Earth didn't just happen to be in the habitable zone. It won a cosmic lottery, possessing all these critical factors. So, the question for TOI-700D and E is, did they win that lottery too? We can't yet image the surfaces of TOI-700D or E, which is why follow-up observations are crucial. These observations will help us determine if they have atmospheres at all. The big unknown is whether TOI-700E has an atmosphere, and if so, what kind of atmosphere it might be. Without an atmosphere, the planet would be a cold, airless rock, much like our own moon. But if it possesses a thick, swirling cloud deck, everything changes. Atmospheric circulation could redistribute heat from the star-facing side to the perpetually dark side. This could create a more temperate zone along the terminator, the line between day and night. Imagine an endless twilight world where the sun never truly rises or sets, but hangs perpetually low. Such a world might feature vast oceans and massive ice caps, driven by a unique water cycle. Life in such an environment could be truly alien, adapted to constant dim light and extreme temperature gradients. Perhaps strange plants would thrive, utilizing the unique light spectrum of a red dwarf star. Or consider another scenario, a thick atmosphere, rich in greenhouse gases, creating a runaway effect. This could lead to a superheated, Venus-like world, with crushing pressures and scorching temperatures. Or perhaps TOI-700E once had water but lost it, becoming a dry, cracked desert landscape similar to Mars. This could happen if its atmosphere was stripped away by stellar winds or other geological processes. The possibilities are vast, from a frozen wasteland to a steamy jungle, or even a world teeming with life. But that's what makes the discovery of TOI-700E so exciting. It represents a new frontier in our search for habitable worlds beyond our solar system. The discovery of TOI-700E is just the beginning of the story, as scientists delve deeper into its atmospheric composition. Using advanced infrared spectroscopy, the James Webb Space Telescope will analyze how starlight filters through the exoplanet's atmosphere. This technique, known as transit spectroscopy, allows scientists to identify molecules like water vapor, carbon dioxide, and methane. The recent discovery of sulfur dioxide in the atmosphere of exoplanet WASP-39b indicates active photochemistry beyond our solar system. For TOI-700E, scientists will meticulously search for biosignatures, such as oxygen and methane, which could hint at the presence of life. However, the definition of biosignatures must protect against false confidence, considering the full range of abiotic chemistries that may produce false positives. Large ground-based observatories play a crucial role in this search, complementing space-based telescopes with their immense power. The radial velocity method, which detects a star's slight wobble caused by orbiting planets, is another key technique. Spectrographs measure shifts in the star's spectrum to determine a planet's presence and mass, revealing worlds we cannot directly see. The discovery of multiple habitable zone planets significantly increases the value of several key variables in the Drake equation. This equation estimates the number of communicative extraterrestrial civilizations in our Milky Way galaxy. Factors include the rate of star formation, the fraction of stars with planets, and the number of planets per star capable of supporting life. Other variables consider the fraction of suitable planets where life appears, intelligent life emerges, and civilizations develop detectable technology. Finally, the equation accounts for the length of time such civilizations release detectable signals into space. Panspermia, the hypothesis that life could be distributed throughout the universe via cosmic dust and asteroids, offers another perspective. While panspermia doesn't explain life's origin, it focuses on methods that may distribute it within the universe. And TESS isn't done. The Transiting Exoplanet Survey satellite continues its mission to find new worlds. As astronomer Alison Youngblood states, we're getting better at finding worlds like our own. The future of exoplanet research is bright, driven by dedicated scientists and powerful instruments. From analyzing distant atmospheres to charting potential pathways for life, our understanding of the cosmos is rapidly expanding. Each new discovery brings us closer to answering humanity's oldest questions about our place in the universe. 100 light-years away, two worlds orbit in the habitable zone of a small red star. We don't know if they have atmospheres. We don't know if they have water. We don't know if life exists on either of them. But we know they're there. We know their size, their orbits, their star. We know they're worth studying, worth watching, worth the years of telescope time and data analysis it will take to understand them. TOI-700D and E represent something profound, the possibility that Earth-like worlds are not rare cosmic accidents, but common features of planetary systems throughout the galaxy. 4 planets, 2 habitable zones, 1 extraordinary system. And somewhere in the data TESS is collecting right now, there might be another system just like it, waiting to be discovered. The search for Earth 2.0 continues, and we're getting closer. If you enjoyed this, don't forget to like and subscribe for more mind-blowing science.